let us go forward. So we discussed how at this point, which is called rich point, peak flop equals to EI into memory bandwidth. Okay, so here we have made this graph for let us solve this question. Consider a roofline model whose rich point has x and y coordinates as following. Now find the performance if EI equals to certain value, and also tell whether we are in a bandwidth bound or compute bound region. So now, first of all, let us solve this. So if rich point has this coordinate, that means you can fill it that this point is at x-axis it is 7.11 and at y-axis it is 204.8. So this means that the peak performance that this processor can provide us is 204 gigaflop per second. That is the maximum performance it can provide. Now, first of all, because EI value of this one, because 1/14 is less than 7.11, that means we are in this region, right? We are in a memory bandwidth bound region. So first of all, let us find out what is the memory bandwidth. So EI into bandwidth equals to peak flop at this rich point, right? At this rich point, as we showed on the previous slide, at this point, AI is given as 7.11, peak flop is given as 204.8. Now the bandwidth is 28.8. Okay, so now because we are in this region, so the performance here will be given as EI into bandwidth. Okay, so in this region where this is line, a straight line, the slanted line, here the performance is given as AI into bandwidth. So the more your AI is, the more performance you get. However, if your AI crosses 7.11, then further increase in AI does not increase your performance because you have already reached the maximum performance. Okay, so going on with the question, because our AI is very low, the performance we are getting is 2.057 gigaflop per second, somewhere suppose here. Okay, so although this processor can give you up to 204 gigaflop per second, but because this application has such a poor value of AI, because it has such a poor value of AI, we get very small throughput, right? We get very small performance. So now you know that for this particular application, see, this AI is for a particular application, and this Roofline model is for a particular processor. So because this application has very poor value of AI, that's why it doesn't get very high performance. Whereas if there was a different application which has a much higher value of AI, suppose here or here, that application can get much higher performance on this processor. Okay, and any questions? I hope this question is clear. Okay, so now let us see how to find the AI, right, for a particular code. So suppose we have this code given, right? Suppose we have this C++ code. I think this very simple C++, I hope you should be able to understand. So here we have this for loop which goes, and here we are, multiplying a certain constant with one array and adding it to another array. So one thing you always have to remember, we only take into account how many memory accesses have been made. Okay, so these loop variables like I or n, they need not be fetched from the memory. They are already stored on chip in registers. Similarly, this alpha is a constant. We don't need to again and again fetch it from memory. We assume that it is already there in the register. So we just have to worry about both read and writes. Okay, memory access means we have to take into account both read and write. This is one point you have to remember. Memory access is not only read. Memory access also means write. So please take into account both read and write. So we have 2 reads, right, for X and Y, and we have 1 write for Z. Okay, so we have total of three memory access. That means for in each iteration we are accessing 3 variables. Now assume each variable takes 8 bytes. That means suppose it is double. Then in each iteration our memory transfer is total of 24 bytes. Okay, our total we are accessing 20 bytes of data from memory, either for read or write. Plus we are doing 2 flops in each iteration. Can somebody tell me which are the 2 operations we are doing?
Read and write.
What are the arithmetic operations we are doing in each iterations? I said we are doing two
Addition and multiplication.
Yes, yes. So we are doing 1 addition here, and we are doing 1 multiplication here. So 2 flops in each iteration, and in each iteration we are transferring 24 bytes. Okay.
And sir, one comparison too for I less than n.
No. We don't take into this. We don't take this into account. Actually, that way you can also say we are adding here. So these are not counted. These are loop control instructions that we don't count. We are saying that we have to see the operations being done on the data that we are fetching from memory. Okay. Look, that's what Roofline model measures. Okay. So now let us go back and see what was the definition of arithmetic intensity. Just here. So total flops divided by total DRAM byte. That means if we fetch every byte of data that we fetch or store to DRAM, how many operations we do on them. That is the arithmetic intensity. So that's why we defined it as follows. So if you 2 divided by 24. So that value comes out to be this. Okay. Of course, here actually the rich point is not given. So to say whether it is memory bound or compute bound, it's insufficient information actually. But there was one more question which I removed. So actually from that we have shown that it is memory bound. And unless we know what is the memory bandwidth, we can't really say whether this is memory bound or not. But that information was there. There was one more question which I removed. There was some more information. So based on that, we are saying it is memory bound. But just by seeing a particular value of AI, we can't say it is memory bound or compute bound. We also have to know what is the rich point. So now again, is this question clear? Okay. Yeah, here actually, yeah, that part is given. So that's why we are saying memory bound. What is exact value, that is not shown, but it's given in the question that this is less than the rich point. This AI value is less than the rich point. Okay, so now let us do this computation. This is already done, but we are showing now you know that LXNet has 5 convolution layers and 3 FC layers. Okay, now here what we have done is for each layer of the LXNet, we have found out how many parameters it has. That you don't have to worry how we found out, you just take these numbers. Okay, how many parameters? That means how many weight each layer of LXNet has and how many computation it is doing in the inference phase. That means in the forward propagation phase, how many actual computations it does. Okay, that's what we found out for each layer. From this, you can easily find out the AI, right? AI is you divide this computation by the number of parameter into, so you assume that each parameter is 4 bytes. Okay, so you take this flops on the numerator, and denominator will have number of parameters multiplied by the size of each parameter, which we assume 4 bytes. Okay, so here, and one more thing we are showing is the overall number of parameters. So just in case you want to show what is the overall behavior. So this is the layer-wise behavior. Yeah, this is the layer-wise behavior, and this is the overall behavior. So one thing you can say is that in the convolution layer, we are doing much more computation, but we have very few parameters. Whereas in the FC layers, on each parameter, we are doing one computation. Okay, in FC layers, on each parameter, we are doing a lot of computations, whereas in FC layer, on each parameter, we are doing very few, just one computation for each parameter. Here we are assuming there is no batching. Okay, so we can see, first thing we can see is the arithmetic intensity varies greatly across the layers. Plus AI of convolution layer is much higher than that of FC layers. See, for sake of simplicity, you assume that each parameter is just 1 byte. Okay, let us make things simple. So here the AI of FC layer is all just 1. Right? AI of FC layers is all 1. Whereas here, as you can see, number of parameters is very few, but number of computation is too much. So here the AI will come out to be much larger than 1. Okay, so as we already said, convolution layers are compute bound, FC layers are memory bandwidth bound. So that is also becoming clear from these numbers if you just compute the AI. Because for FC layers, AI will come out to be very small. For convolution layers, AI will come out to be very large. Is this clear? Any questions? Okay, let us go forward. Here I have not actually shown you the AI, but you can just do the mental calculation to just get an idea of how much large the value will come out to be. Okay, so this was assuming that we have no other bottleneck in the system. Now we will add those bottlenecks and then see how much performance will change. So we'll take the example of AMD's Opteron processor. This is certain model. Okay, so it has dual sockets. So this is one socket. This is another socket. Okay, it has some prefetcher. What that is, don't worry. I will explain just the key idea a little later. Now it has eight cores total, right? 4 cores are here. Okay, 1, 2, 3, 4, and 4 cores are here. So total 8 cores. It has a frequency of 2.3 gigahertz. Okay, it is two-way SIMD, right? That means the vector length is 2. Okay, vector length is 2. So SIMD is vectorization. So how much is the vector length? Vector length is 2. So that's why it's called two-way SIMD, and it performs double precision operations. Okay, so this is conventional CPU. In conventional CPUs, we mostly rely on double precision, but in deep learning accelerators, they are going for very low precision, as we'll see in more detail a little later. Okay, now it has FPMUL means floating point multiplication. This is floating point addition. So it has separate data path for floating point multiplication and floating point addition. And every floating point operation takes 4 cycle latency. Okay, so if you could not understand all that, that's not so important. We will understand more important point little just now. So here just we've written the specifications of the Opteron. Now we'll see that how each of them is very important to achieve the peak performance. So here it has a peak double precision performance of 64 gigaflops. Okay, so how do we obtain this peak performance? I will show. Let us show that first. I will just a minute. I will. So here, let us see for this how we assume the peak flop. So suppose this is a KNL. KNL is some processor. It's a Knight's Landing. So it has certain frequency, 1.4 gigahertz. Okay, plus it has a vector width of or vector length of 8. Okay, it has a vector length of 8. Plus it has 2 VPUs. Okay, each core has 2 VPUs. I mean, so sorry, that the KNL has 2 VPUs. Now each VPU has 68 cores. Okay, and in each cycle it can do one FMA instruction. Okay, each core. Okay, each core can perform, or actually I think it has every core has two VPUs. I will confirm. So whole point is you find out first of all how many resources it has. So it has frequency of 1.4 gigahertz. It has a vector width of 8. It has 68 core. Each core has two. Yeah. Now I remember. Each core has two VPUs, and each VPU can perform one FMA instruction in each cycle. So because one FMA means fused multiply add. So FMA is counted as two instructions, multiply and add. That's why this number of 2 came. So that's why it can perform. That means with a peak, its peak performance is 3 teraflop per second of double precision. Because this vector width is for double precision, because it has actually like double precision is 64-bit, and it has 512 wide data paths, 512 bits data path. I mean 512-bit wide data path. Now, if your operand is 64-bit, then vector width is 8. So that's how we got 3 teraflops per second for double precision. Okay, in this way we find out the peak performance. So in this similar way, we have here also in the Opteron also we found out the peak performance. So here suppose bandwidth is 2.3. Then we have 8 cores. Now it has two-way SIMD. This is already almost 32, right? Plus each core can do, because it has separate data path for FEML and FPAD, it can do both of them in a single cycle. So you have to again multiply by 2. Okay, so this is almost 64. Okay, this is almost 64. So that's how certain peak performance is there. So that's why peak gigaflop per second is 64. So now we may assume that you may get this performance, but no, you can't get this performance. First of all, we already have discussed that DRAM bandwidth will be a bottleneck. You will have certain DRAM bandwidth. Okay, so that's why if your AI is small, you can't get this peak performance. Your actual performance will be less. And if your AI is less, then your performance is also less, because now you're bottlenecked by the DRAM bandwidth. So here, this Roofline model is plotted on a log scale. That means log scale on X, log scale on Y. Okay, so now this is again maximum. Your actual performance will be further down. How? Let us see. So here, Opterons have dedicated multiplier and adders. Okay, so if your code can utilize both multiplier and adder, then you can get this peak performance. Okay, but suppose your code is such that it only does addition, it does not need the multiplication. Okay, suppose it does not need the multiplication, then the multiplier hardware is remaining unused. Right, your multiplier hardware is remaining unused. So then your actual performance will not be 64, it will be half. Okay, so this is like you have, like, although my roof is here, but suppose I put some tent, then the height is further reduced. That's why it's called ceiling. So this ceiling is like a constraint on the performance. So instead of this, your performance is reduced. That means you have all the hardware resources, both adder, multiplier in all the cores, but you can't use them because your application does not need it. Okay, so you're only using, suppose adder, or if you're only using the multiplier, then it will be half. Further, suppose your this was Opteron, right? So Opteron had two-way SIMD, right? That means if you're double precision, so double precision is 64-bit. So 64-bit into 2. So that is 128. Okay, that is 128. So now, if that means that's the 128-bit data path. Now, if your instruction they are not SIMDized, right? That means if your code cannot use the vectorization capability, then further performance will reduce. Okay. Further, the performance will reduce. So attainable performance will be further reduced. Now, similarly, on Opteron floating point instructions have a 4-cycle latency. Okay. Now, if your code does not have 4-way ILP, that means ILP is instruction level parallelism. That means how many instructions a core can execute in parallel. So if you can't exploit that ILP, then performance will further reduce by 4 times, right? Instead of having 4 floating point instructions going in the same time, you are having only 1 floating point instruction going in a time. Okay, so that's why your performance will further come down. So in this way, you can see that so all these are called computational ceilings. Okay, all these are called computational ceilings because this limits the peak level. This is the computational performance that you are reducing gradually. That's why it's called ceiling. Now let us see communication ceilings. Right, that means your memory bandwidth, effective memory bandwidth can also come down. So we can perform a similar exercise, taking away some parallelism from the memory subsystem. So here, this peak bandwidth was assuming that some prefetcher was working properly. But if your prefetcher is not working properly, then you fully utilize the bandwidth. It is just like that. Suppose your road has 10 lanes. Okay, it has 10 lanes, but at any particular point of time, only 8 cars are running. Then those 2 lanes are not utilized. Your effective bandwidth is only 8 lanes, not 10 lanes. So you are now achieving less parallelism. Instead of 10 lanes, you are achieving only 8 lane worth of parallelism. That's why your effective bandwidth is reduced. Similarly, Opterons are NUMA, right? We showed that Opterons are NUMA. How? So here, these are NUMA. This is one NUMA node. This is another NUMA node. So now, if you are able to utilize only, I mean, here actually what happens is that, see, you see what is a NUMA node? So NUMA node means, let us see what that is. See here we have half of our DRAM is here, half of our DRAM is here. Okay. Now if one of the cores, suppose this core, right, this core, if it needs the memory from this, that's called a balanced design. But if this core needs a memory that is, I mean, or a data element which it needs to get from here. Okay, so that is called unbalanced NUMA node. Why? Because first of all, you need to fetch data here, so that will be 10 gigabyte per second. Plus, afterwards, this data will come here. That is much slower, 4 gigabyte per second only. Okay, so it takes a lot of time to get the data if the data you need is not in the same NUMA node, but it is in the DRAM of another NUMA node. Okay, so that makes things very slow. So that's why effective, if you're not doing prefetching, then further bandwidth goes down. If you don't have a NUMA node, I mean, if it is not balanced, if the memory traffic is not correctly balanced among the 2 sockets, then further memory bandwidth will go down. Okay, so how you could further, if you could further add some more ceilings, right? If your accesses are not continuous, if they're random accesses, then further the bandwidth will go down. Okay, so that's the idea. So in this way, effectively, what you are assuming the performance to be the highest peak, your actual performance will be much less because of these practical constraints. Okay, so in this way, so here now we have imposed both computational ceiling and communication ceiling. So, and any questions here? I will actually in Roofline model, I will also discuss a lot of solved examples that will make things more clear. But so this is already I'm discussing like 2-3 solved examples because the definition of Roofline model is very straightforward. How to apply this Roofline model, that is more challenging. So here, I hope I have made some things clear through this example. And any questions? Yes, Priyansh.
Sir, can you please explain memory prefetch again?
Okay, yeah, prefetch I did not explain. So see what happens in the prefetch. Suppose let us take this idea. Suppose you you go to library. Okay, you go to library. So you get the book that you need in the first semester. Okay, so the instructor tells you that you need this book, so you go there, right? It takes you suppose 1 day to go there, 1 day to come back. Okay, then in 2 days you get the book. Now one option was, so that means suppose the classes started on the 1st of some month, and on the 3rd of that month you get the book, right? So you're delayed by 2 days. Another option was you could actually really estimate, okay, this course is coming. Now I would need that book. So instead of issuing your request on 1st of that month, suppose 1st August, you issue your request on the 30th July itself. Okay, so 30th July and 31st July. So on 1st itself, you get the book. Instead of getting the book 2 days late, you prefetch means you expect what will be required in the future and then you prefetch it. You don't wait that only when the demand comes, I will issue a request. Just like e-commerce, right? You purchase something on e-commerce. It's not that, I mean, if you can predict the demand, okay, I would need that, winter vacation is coming or the winter season is coming, so I will need some, woolen clothing. So you pre-order it. I mean, you order it well in advance so that when you need it, you already have it. So pre-fetch just means it's not a demand fetch. That means not that only when you need it, then you are fetching it. Prefetch means you expect the future demand and then you prefetch it. So similarly here, what happens is our computers also have either hardware prefetcher, software prefetcher. What they are, that's not how we are doing prefetch, hardware, software. That is not very important. Prefetch word is important. Okay, so if we have prefetch capability. Okay, so the software prefetch means in the code itself we write down, we give some instruction to the hardware that now when you are at line number suppose 30, then prefetch the data which will be required at line number 40. We are telling the hardware. Okay, when you are executing line number 30, we are telling the compiler when you are at line number 30, prefetch the data which will be required at line number 40. So that is the idea of prefetch.
Okay,
if you don't have this, then your code will be slowed down, right? When you come to 40, then you will issue a memory access instruction, then you will stall, you will wait. Okay, is it clear?
Okay, sir. Yes, sir.
Any other question, please? Okay, so we'll go forward if you don't have any question. So now let us see this same. We'll now do this analysis again, right? The ceiling idea. So first of all, here, this is the peak performance. Suppose it is given the peak performance is 3 teraflops per second. Now you're seeing that this peak performance is coming because of frequency being something, vector width being this, using both VPUs, being able to execute FMA and utilizing all the 68 cores. But see, you hardly have any, at least the application that we run, it will not utilize all the 68 cores. It will utilize maybe 1 or 2 cores. Okay, so your actual performance will be much less. So that's what we'll try to show here. So here I'm only showing the computation ceiling. So suppose this is the peak double precision performance, which comes from this. Okay, now, so this was our peak. Here we assume 1.4 gigahertz of 1.4 gigahertz of frequency. Okay, so, but sometime it happens if you are using all the 8 vector lengths, you can't run at 1.4 gigahertz. You will be able to run only at 1.2 gigahertz. Okay, because if you run at very high frequency, you also dissipate a lot of power. So to avoid exceeding the power budget, the hardware will actually throttle your frequency. That means it will reduce the frequency. So instead of 1.4 gigahertz, it will reduce the frequency to 1.2 gigahertz. So already instead of 3000, you have come down to 2600. Okay. Next, core ceiling. So if you don't have sufficient instruction level parallelism, okay, then you are not able to utilize both the VPUs. Okay, and you're also not able to utilize FMA, right? That means you can't, in a single cycle, you don't need both add and multiply. Suppose your code is dominated by add, it only needs to do add, or it only needs to do multiplication. Then you are not able to utilize both add and multiply. So you remove the factor of 2 from this, and you also remove the factor of 2 here. So compared to this, you already reduced by 4x. Similarly, if you don't utilize this vector width, suppose your program is such that it does not need vectorization capability, it is just a simple scalar application, then your further your performance will go down, right? 8x reduction in the performance. Okay, so that's the whole idea. That means if your code does not utilize all the resources, then it will achieve very small fraction of the total performance. Okay, is it fine? And similarly, so this was computational ceiling. So this was like here, the same idea, computational ceiling. Similarly, here it was for DRAM bandwidth. Suppose instead of DRAM, suppose if you could actually, so this KNL has actually L1 cache, L2 cache, and before DRAM it also has MCDRAM, which is higher bandwidth than DRAM but less bandwidth than L2. So if your data resides in DRAM, then you will face this ceiling. Okay, but suppose your program is such that all the data that you need is already there in the L1 cache. Okay, all the data that you need, it's already there in the L1 cache. Then you are not at this ceiling. You can get much better performance, because you don't have to go all the way to DRAM, which has very slow bandwidth. You can get the data from L1 itself. So your effective memory bandwidth is much larger. Okay, or if your data is in L2, then it is not as good as the data being in L1, but at least it is good enough. Or if your data is in MCDRAM, again it is better than having it in DRAM, but worse than having it in L2 or L1. Okay, so effective bandwidth, you have to see how much bandwidth you're getting. That will decide how much performance you will get. Okay, if there are no questions, yes, please.
Sir, in the graph, sir, if we like here, we are saying if our memory was stored in cache. So,
No,
sir, if we don't...
no, wait. If the data that a particular application needs, if all that is already available in the cache, then you fetch the data from cache itself. You get much higher bandwidth. But so it's just like that. Suppose all the books I need are already there in my bag. I don't have to go to library.
So, yes, sir. So it increases our memory bandwidth, but it doesn't increase our computational bandwidth, right?
Yeah, it doesn't increase the computational bandwidth. Yeah. Computation is decided by how much compute power you have.
Okay.
Any other question? Okay, so let us go forward. Now I will just illustrate Roofline model of different processors. So here, this is just a simple comparison of different processors. Although you don't know them, so it doesn't, don't worry what they are. Slowly we will explain some of them. So here, this is a CPU, the green one. Now this is GPU, the blue line. Okay, Google's TPU, which is probably we'll discuss next week. Next thing is something the next thing I will discuss is Google's TPU. So that is this light blue, right? This one. This is the highest ceiling, and this is an FPGA. Okay, so FPGA here you can do it with either 16-bit, 8-bit, or 1-bit. So 1-bit is second highest. Although FPGA does not have a lot of resources like a TPU, but if you can go to a lower bit width, you can get a lot of performance. I mean, the effective bandwidth becomes high. So here, the whole idea is, so again, this is just for processor. We don't have AI because we don't know the application. Okay, so this is all for data center scale systems, and this is for embedded scale. Okay, embedded just means, for example, like small budget systems. For example, TPU, for example, GPU will have a power budget of 300 or 400 watts. Google's TPU There are 4 versions of TPU, so the power budget goes from I think around 100 watt to 400 watts. FPGA, the actual power budget, actual power consumption depends on how much resources you use. So that's why you can't say it. And Haswell CPU would have like maybe 150 watts to 200 watts. Now TX1 will have a power budget of 15 watts. I don't know the power budget of DSP and this, but usually they are very small. Okay, so this is the ultra scale. This is the high-end FPGA. Okay, and this is the low-end FPGA. Okay, this is the low-end FPGA. So here you can see that first of all, let us focus on the left side. So TPU has much higher ceiling, right? So if you just compare, this is like around 1, this is around 100. So almost like 100 or 80 times higher performance. TPU provides almost 80 times higher performance than the CPU. I mean, it has the potential to provide 80 times higher speed up than the CPU. And also it has higher performance than the GPU also. Similarly here, FPGA with 1 bit has the highest. Second highest is FPGA with 8 bits. Then least is this TX1. Okay, TX1 is the lowest. Okay, so for each of this processor, you can find out the Roofline model. So now what is the idea of Roofline model? See, here we don't know which application we will use, but it's a generic model. At least it gives us the idea. Okay, what is the maximum capability it can provide us? Okay, if an application does not utilize all the resources, your performance could be this. See, it can happen that, for example, like you run anything on TPU, but it has very low AI, so it gives only this much performance. Whereas you run something on CPU, you get much higher AI, so your performance is here. So it may happen that on CPU you can get better performance than that on TPU, even though TPU has a higher ceiling. Yeah, it has a higher peak throughput, but how much of that you are able to use depends on the application. Okay, so this Roofline model is not everything. It gives you half of the idea. Half of the idea you have to get by seeing the application. Okay, so now let us see. Anyone has any question here? Okay, so now let us see what are the how Roofline model allows us to decide which optimization is best for a particular processor or for a particular application. So let us see. Let us assume that as if this is the original Roofline model. Okay, so here this is the DDR. That means the DRAM bandwidth. This is the peak flops. If you don't use FMA, then our performance comes down here. If you don't use the vectorization, performance comes down here. Now, first thing is, suppose our performance is here. Okay. Now, as you can see, we are hitting some ceiling. Our roof is very high, but even before hitting the roof, we are hitting some ceiling. So now we are at this point, right? This circle. So here, what we can do, we can vectorize, right? It's already written here that because we were not able to vectorize, that's why our performance is less. So what we need to do now, we need to vectorize. We can either do compiler or we can write the code differently. So right now, if we are at this point, our goal should be to increase the performance and go in this direction. If we are at this point, okay, that means we are not hitting the computational roof, we are hitting the communication ceiling. So we should now try to hit this. So for that, we can improve the memory bandwidth. So this ceiling was because we were having this NUMA effect. So instead of storing the data in the second NUMA node, we can bring the data to this NUMA node so that this NUMA ceiling is removed. Okay, and if we are already at DRAM bandwidth, okay, that is our current AI is here. So we should move towards this, right? We should try to increase the AI for this particular application. For this particular application, let us try to increase the AI so that we can get higher performance. Okay. So here, how do we get it? We try to reduce the number of times we access the memory. So we already discussed what is cache blocking. So if we do the cache blocking, the number of cache misses are reduced. So we don't need to all the time go to DRAM. So in that way, we can we can reduce the number of accesses to DRAM, so our AI will improve. Okay, so the whole point was this was 3 broad categories of optimization. What are the optimization we can do seeing the roofline model? So these are the optimization. If our AI is low, try to improve the AI. If we are not hitting if we are not already hitting the our memory band DRAM bandwidth, let us try to get that DRAM bandwidth. And if we are having somewhere here where we are not bottlenecked by the memory bandwidth, but we are in a compute bound region. Okay, if you are in a compute bound region, then try to improve the computational performance by doing vectorization or using FMA or using both, or boosting the frequency. Okay, so that's the idea. So, any questions here? See, this roofline model will be very, very helpful. Suppose you're an architect. Now you are designing some processor for suppose NVIDIA, Intel, whatever. Now you don't know which application will run on it. So without seeing the application, what is the best you can do? At least I can design a processor which has as high roofline as possible. That's why this roofline model is very important. So let us take an example. So suppose here, this is just an example of what we discussed on the previous slide. So if you are, this is the, if you remember, this is a KNL. Okay, so this is the, 1 minute. This is the same figure which I'm showing there, but without writing this CPU and bandwidth, which bandwidth it is. We are now seeing that figure now. Okay, so suppose your application performance is currently here. Okay, so as you can see, its AI is very, very low. Okay, its AI is very, very low. So now first thing we'll try to do is we will try to improve the AI. Okay, so we will try to, so currently it is DRAM bandwidth bound. Okay, so what we do, we implement certain L2 cache optimization. Okay, so suppose originally we were able to not fetch the data from L2 cache. All the data fetch we are doing was from DRAM. So we try to bring the data in the L2 cache itself so that we don't have to go to DRAM. So now our AI improves, right? So the roofline model, this model moves to the right. Okay, because our AI is improved. So instead of operating it at this point, we are now operating at this point. Okay. Similarly, now we can suppose if you could some further improve the AI. Okay, this is still the same. This is the same category of optimization. This still this category of optimization. Both this. If we did optimization with L2, then we did optimization with L1. So again, our AI comes here finally. Okay, we improved the AI somehow maximum. Now we are hitting the computational ceiling. Okay, so now we can go in this direction. Okay, so this first case was for the memory bound application. So we tried to come out from the memory bound region. We tried to come out to compute bound region by increasing the AI. So we did 2 optimizations, one for improving L2 utilization, another is L1 utilization. So we improved the AI value. So we came to the computational bound region. Now in the computational bound region, we'll try to go in this direction. So our AI is already very, very high. So there is not much we can do by increasing the AI, right? At this point, if we increase the AI, we don't get much better performance. Okay, so it is compute bound region. It is not using vectorization or FMA, or it is not using both the VPUs. So what we'll do, we will implement the vectorization. Okay, we will improve the vectorization. So because we have not changed the AI, right? We have not changed the AI, so we don't go right or left. We are in the same region at this point itself. X coordinate does not change. So we implement vectorization. Okay, so our if suppose we utilize all the 8-fold vectorization, our performance improves by 8 times. And if we can utilize FMA also, Okay. So then further our performance doubles because FMM is multiply add. If we are able to utilize both multiplier and adder, our performance just doubles. Okay, so in this way you can see how we were originally at this point. By doing all the optimizations, we finally reach the peak performance which we can get on this processor. This is how we will work. So another optimization we can do is we can lower the precision. So here you can see for LXNet. So here this is the AI for, I mean, this green line is the AI if we use 8-bit. If you use the 8-bit, operands, and this is the performance we'll get if you use 1-bit for all the parameters. So then this red one is the 1-bit ops, right? So our AI also improves and our ceiling that we are attacking is also high. Okay, we are now able to achieve much higher throughput. So instead of achieving only less than 1000 gigaflop, now we are achieving maybe 10,000 gigaops. Okay, maybe more than 10x improvement in the performance. Okay, so for LXNet, compute bound performance for binary operation is 16 times better than that of 8-bit fixed point. And it is better than, it is 53 times better than that of 16-bit fixed point operations. So in this way, you can see one optimization we can do is precision. See, lower the precision. See, one optimization we did here was to use the caches in a better way. Here, and one optimization here we did was utilize the vectorization, utilize both VPUs, utilize the FMA unit. So these are all different optimizations. Here, similarly, another optimization is that we can lower the precision. So now we need to fetch, although we are fetching the same number of parameters, but each of them is very narrow, just 1 bit. So now we can fetch many parameters in a single access. Okay, any question on this figure? Any questions here? So here two things are happening. One is that system, that means the hardware, that means our FPGA, that has 3 different roof lines. One for 16-bit operation, one for 8-bit, one for 1-bit. And similarly, our LXNet model also has one value of AI for 8-bit and another value of AI for 1-bit data. Okay, so that's the idea. So, and similarly, you could do all other optimization. But so we have already discussed what is cache tiling. So initially we were here, we were not doing tiling and we were not doing any code optimization. When we did tiling, so instead of here, we moved here. And when we also did code optimization, so we moved here. So this is from a certain figure. This is just a summary of, this is a repeat of what we already shown. This is taken from a paper. So I just wanted to show how many. So the whole point is they are writing some research paper and that they are showing that originally the Roofline model was here. Then we did this optimization. So the AI improved. Then we did further optimization. Then further the performance improved. Now, finally, let us discuss one last example. How Roofline model helps us in designing a balanced processor. So suppose you are an architect for suppose Intel. Now, suppose you have this Roofline model given already. OK, and you have an application which has this value of AI. And as you can see, currently this application is compute bound, right? Because it's if this AI was less than this value, then it would be bandwidth bound. If its AI is more than this, then it is compute bound. Okay. Now, suppose you are the architect who was working on the processor. You take the original processor, you boost its core performance, right? Suppose you double the number of cores. Okay, or you make the cores 4 times, 8 times, whatever. Okay, so you just boosted the core performance. You did not change the memory bandwidth. You just boosted the core performance by increasing the number of cores. Okay, now you can see the ceiling, the roofline model shifts here. Now the code which was previously compute bound, now it has become memory bound. Do you agree or not? Right? Is it clear? Previously we were in a compute bound region. Now we are in the memory bound region. Okay, so the whole point is, if you optimize only core, that means if you only optimize the core resources, but you ignore the memory, then still you are not achieving the peak performance. Right? After boosting the core performance, you expect, okay, my application will achieve at least this much performance. But actually you are achieving only this much. You are not achieving the full performance. Why? Because you did not optimize the memory bandwidth. So that's why you have to do both. So we'll show this example. Remember this example. We'll show this when I discuss the TPU version 1. TPU version 1 was bottlenecked by memory. Okay. Although they have very good compute, they have a good systolic array. So it does computation very nicely. But because the memory was a bottleneck, it did not achieve very high performance. That's why in the next versions, they improve the memory bandwidth also. Okay, so you can't just throw a lot of cores. If you're not having memory, then those cores will remain idle. Okay, so that's why we need to optimize both computation capability and memory capability. That means memory bandwidth. Only then the total performance will increase.